Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 45. We are discussing design of low speed contra rotating fan. So this is what configuration we have decided for our design problem. Now here in this case we have selected this contra rotating fan. That's what is having aspect ratio of 3. That's what is little different from what conventional design what we are expecting. So if you recall, this is what will give you idea. Say for low speed axial flow compressor we have taken our aspect ratio of 1. Here we are considering our aspect ratio of 3. Now this is what all we have discussed in sense of our hint for solving the problem. So what we realize, we will be calculating our mean diameter for rotor 1, then all parameters that will be calculated at mid station. Based on our design concept or design fundamentals, we will be opting that for say different stations for this blade. Now for rotor 2, as we have discussed, say for conventional stage, what absolute flow or absolute velocity coming out from the rotor, that's what we are assuming to be going to the stator. So in line to that, here we are making our assumption the velocity which my flow that will be coming out from rotor 1, that's what is say absolute velocity, that's what will be entering inside my rotor 2. Okay, so we can say our velocity C2 and velocity C3, they both are same. In other sense, we can say my absolute flow angle alpha 2 and alpha 3, that will be same. Then based on this assumption, we will be doing our calculation at the mid station. Once we are having the calculation at the mid station, we can do our calculation at different locations along the span and we can make our blade ready. And that's how we will be moving with say design of this contra rotating fan. Now very first thing, let's take with say my rotor 1 design. Now if you recall, in order to have this rotor 1 design, we need to have some velocity components that need to be known to me. So if you recall, our general guideline or basic guideline what we have discussed for the design of axial flow compressor, it says maybe mass flow rate, or we can say my flow coefficient, or say my diameters. If that's what is known to me, I can move with the calculation of say initial parameters. For this design, if you look at what we know is mass flow rate, that's what is known to me. My tip diameter also is known to me, and rotational speed for both the rotors for design we have taken 2400 rpm. So that's what is making our calculation little easy in sense of say assumptions. If you recall, we have designed our low speed axial flow compressor where we have assumed our say CA by U tip to be say some number. So here in this case it is not the case because we know our mass flow rate. So let's move with the calculation. What we know, say we know our tip diameter is 0.405 meter. Okay, and our aspect ratio, that's what is given, it is 3. Even chord for these blades, they are given, it is say 45 mm. So we can say this is chord, it is say 0.045 meter. If that's what is known to me, say my aspect ratio we can define as a height to chord ratio. You can see this is my height to chord ratio. Now this height we can write down, that's nothing but my tip diameter minus hub diameter divided by say my 2c. Okay, since I know what is my aspect ratio, we can do calculation for hub diameter. And here in this case, if you look at my hub diameter, that's what is coming 0.135 meter. So you can understand, if you are not known with the aspect ratio, you can assume your radius ratio. By that way also you can do your calculation. Okay, so initial case, if it is known to you, better you go with that part with the known parameters. If not, then make suitable assumptions. Okay, and accordingly we need to move forward with. Now once my hub diameter and tip diameter, they are known to us, we can do the calculation for the inlet area. You can say it is nothing but pi by 4 my tip square minus hub square. Okay, and that's what is giving me my area to be 0.114 meter square. So this is what is the area in which my air, that's what is going inside. Now this area, you can understand, we know our basic continuity equation. It says by mass flow rate we can write down as a density into area into axial velocity. Basically we are looking for our velocity component, we are looking for axial velocity. So this axial velocity we can write down, that's nothing but m dot by density into area. Let's make the assumption, say density we can assume safely for our atmospheric condition as 1.18 kg per meter cube. If we are putting mass flow rate, that's what is given to us, it is 6 kg per second. So 6 divided by this, that's what is giving me my axial velocity to be 44.4 meter per second. Now this is what is my axial velocity, that's what is known to me. Here in this case, like there is always confusion with total property and static property. Say we are considering our static temperature, that's what is given, that is 298 Kelvin. So just careful, if this is what is specifically been mentioned as a static temperature, then it's better you do calculation for say total property, and that's what we have done here. Say thermometer, that's what is giving me my atmospheric temperature to be say 298 Kelvin, that's what is nothing but my static temperature. So we can calculate our total temperature as say T1 plus Ca square by 2 Cp, because we can assume or we have our entry of the flow, that's what is axial, and that's the reason my Ca and C1 they both are same. So if you are putting this as a number, it says my total entry temperature, that's what is 299 Kelvin. So now we can say we know what is our axial velocity, what is our temperature. Now my next parameter for making my velocity triangle, that's what is say my peripheral speed. And as we know, we are doing our calculation at the mid station. That's the reason why mean diameter we can calculate as say d tip plus say diameter of hub divided by 2. That's what is giving me my mid station as say 0.27. This is what is say my 0.27 meter, that's what is my diameter at the mid section. Okay. Now once this is what is known to us, we can do calculation for our say peripheral speed. So this peripheral speed we are writing for rotor 1, it is say pi d n by 60. Since my rotational speed for rotor 1 it is giving 2400 rpm, so that's why if we are putting that, it says my peripheral speed, it is coming 33.93 meter per second. So this way you can do your calculation for say Ca as well as U. And as we discussed, maybe if Ca by U tip, that's what is given to you, that will make your life easy. You can go with the calculation straight way. So purposefully this data, that's what has been given, so that you will get the idea how to do calculation if those parameters are not known, and few parameters which are required, that's what is known to you. Okay. Now if we say my outlet pressure, so what we have assumed, say we are expecting our total pressure by rotor 1, that's what is say 1200 Pascal. So we can say my total pressure at the mid station, that's what is say P01 plus delta P0. So this is what will be my total pressure at the outlet. Now, once my total pressure at the outlet, that's what is known to us, we can do our calculation for the pressure ratio for my rotor 1. It says it is P02 by P01, and if we are putting that number, it says it is coming 1.011. That's what is my pressure ratio of rotor 1. Okay. Since my pressure ratio is known to me, we are looking for something. Say, you can understand, say if we are looking for say inlet velocity triangle, we are looking for say 3 different velocities. One, it is say peripheral speed, we are looking for absolute velocity or axial velocity, and we can calculate what will be our relative velocity. Now, in line to that, suppose say if it is having whirl, you can do calculation for CW1, but since our entry it is given axial entry, so my CW1, that's what is 0. But in order to plot my exit velocity triangle, I need to have one of the parameter or the angle, that's what need to be known to me. Okay. So, we are moving towards that. What it says, we can say our isentropic temperature rise, that's what we can calculate here by using say T01, what is my pressure ratio and efficiency. It says efficiency, that's what for 2 rotors they are given 85%. So, we can say this is what is say 85, that's what say my delta T0 in rotor 1, it is 1.18 Kelvin. Be careful what design we are discussing at this moment, that's what it says subsonic design or low speed design. So, this range of temperature that will be coming in a lower side. Now, as we have discussed, now suppose if I consider this is what is say my relative or my velocity triangle at the entry of my rotor 1, since this is what is say axial entry, we can write down my 10 beta at mid station, it is U by Ca. U we have calculated, it is 33.93, and Ca also we have calculated, it is 44.4. So, they are the known parameters here. Okay. If that's what is your case, we can calculate what will be my say air angle or relative flow angle at the entry of my rotor 1. Say this is what is my beta 1. Okay. Now, we will compare our aerodynamic work and thermodynamic work. You must understand, like we are looking for calculation for say what is the outlet condition. So, if we are putting that, it says this is what is my work done factor into UCA 10 beta 1 minus 10 beta 2, that is nothing but my aerodynamic work, and this is what is my thermodynamic work, it is a Cp delta T0. So, this is what we have calculated, and based on that we can calculate what will be my beta 2. So, here if you look at my beta 2, that is what is coming minus 2.44. Okay. So, this is what we are calculating at the outlet condition. Now, what we know, this is what we can say, by using this we can calculate what will be my CW2, because we are looking for all other angles and parameters need to be calculated. So, my CW2, that is what we can calculate by using U minus Ca 10 beta 2. Okay. If this is what is your case, my whirl component at the mid station at the outlet, it is coming 35.82 meter per second. Okay. Now, here in this case, what angle we are getting, that need to be very careful about. So, you can see this is what is a modification of our angle. So, we can say my velocity triangle, that is what will be changing at the mid station like this. Be careful. Okay. So, we need to be very careful when we are doing our calculation. So, this is what say minus 2.44, this is what is say this angle, and this is what will be my CW2. So, if you compare my CW2, that is what is coming to be larger than that of my peripheral speed U. Okay. And if you look at my angle alpha 2, that is what is with my axial direction we are calculating with. Okay. So, be careful when you are doing your calculation, make your velocity triangle accordingly. Now, once we have calculated our beta 1 and beta 2, we can do our calculation for say blade deflection angle, that is nothing but my delta beta. So, if we are putting that delta beta, it is coming 39.83 degree. Okay. Now, say for this design it is given my power or say motor, that's what is available, that is having power capacity of 15 kilowatt. So in order to check whether this motor is sufficient or not, that also can be verified when you are doing your calculation using this program. Okay. Now here in this case we can write down my power, that's what is given by mCp delta T0 by mechanical efficiency, and this is what is my compressor efficiency. Be careful what we are doing at this moment, say we are assuming our mechanical efficiency to be 75%, which may not be the case when we are talking about the actual engine. This may be in the range of 0.85 or 90%. We have discussed this point. So if you are putting this as a case, it says my power, that's what is coming, say 11.21 kilowatt. Okay. So this is how we are doing our calculation for power. Remember this power calculation, that's what is at the mid station. Okay. Now once this all parameters are known to us, we can do calculation for say different velocity components. So if we are considering say inlet velocity triangle, my relative velocity at the entry of my rotor, that can be calculated based on say sine component. So that's what is given by say u by sine beta, and that gives me my relative velocity at the entry as 55.85 meter per second. Okay. Same way, based on my outlet velocity triangle, we can do our calculation for relative velocity at the outlet, and this is what is the formulation for that. It says my outlet velocity, it is coming 44.44 meter per second. Okay. Same way we can do our calculation for absolute velocity, because this is what is my requirement for what is going inside my rotor 2. Okay. So this we can write down, it is Ca by say cos alpha 2, and that's what is coming 57.05 meter per second. Okay. So this is how we are doing calculation for different velocity components. Now once this is what has been calculated, we will check with the de-Holler's factor. It says that is nothing but a ratio of relative velocities. So we can say V2 by V1, and that's what is coming 0.79. So this is what is showing our de-Holler's factor. So one of the parameter for checking, that's what we are considering, is a de-Holler's factor. Okay. Remember one thing, this de-Holler's factor, that's what is applicable for the stage, and that too it's a rotor stator combination or say stator rotor combination. But still we will be checking in order to get the idea what we are claiming in sense of what we are getting for relative velocity at the entry of the rotor 2. We will see this part. Now once this is what has been calculated, a target is to calculate the diffusion factor, and in order to do the calculation for the diffusion factor, we are looking for say parameter, that's what is called M factor. So Carter's rule, that's what it says, my slope factor that can be calculated based on what we say my maximum camber. Okay. And this is what is giving me my say M factor as say 0.41 at the mid station. Now pitch, that's what we are writing as say 2 pi r by z. Now the question here, it is the selection of number of blades. Okay. Since we are planning to compare our design with the earlier design for say different pressure rise, and that's the reason why we are assuming same number of blades. It says for rotor 1, I am assuming here number of blades to be 19. You know better. We are doing our pen paper calculation at this moment. Later on, based on this calculation, we will be making our Excel sheet program, and in that Excel sheet program you can play with this number. Okay. For say sake of brevity, we will be taking same number of blades, say 19 number of blades. It says this is what is giving me pitch as say 0.044. Okay. We can calculate our solidity, it is nothing but chord to pitch ratio, it is coming 1.00. Now once my solidity at the mid station it is known, we can calculate our diffusion factor based on the formula for say beta 1 and beta 2. So if this is what is your case, diffusion factor is coming 0.52. at a mid station. We are presently discussing for say rotor 1. Now, we are more interested in calculating what all will be our angles, say camber angle, my deviation angle and stagger angle. So, let us put, we know based on our equation, this is what is given by delta beta minus incidence divided by this formula. What we realize at mid station, as we have discussed earlier, we are assuming our incidence angle to be 0. Same way at the hub, when we will be doing calculation, we know we are assuming our incidence angle to be positive, and at the tip we are assuming our incidence angle to be negative. So, here we are taking this to be say 0, it says my camber angle, that is what is coming 67.87. Okay. Based on this camber angle, we can do calculation what will be my say deviation angle. So, this deviation angle is nothing but m theta by root sigma. If we are doing that calculation, my deviation angle is coming 28.05 degree. Okay. Once these two parameters are known to us, we can do calculation for say our stagger angle, and that stagger angle is coming say 3.45. Okay. So, this is what all we are doing calculation at the mid station. Let us see. So, we can say this is what is my Excel sheet program or my parameters, that is what is representing. Here in this case, if you are looking at, we are assuming pressure rise by my rotor 1 as say 1200 Pascal. Okay. This is what is say we are considering as say 1200 Pascal, and based on that, these all are the parameters which are calculated. You can say we are having our diffusion factor 0.52, our de-Holler's factor 0.80, and our camber angle, that is what it says 67.88. Now, once this station at this particular station we have done our calculation, we will be targeting what all need to be checked for say my hub station and at my tip station. So, let us move towards that. So, what we realize, say when we are talking about the fundamental design approach, we know we are having great control in sense of putting the aerodynamic loading to my rotor. Okay. We can think of tip loaded rotor, we can think of hub loaded rotor, we can think of mid loaded rotor. So, for present case, we will be considering say tip loaded rotor. Okay. So, when we say it is a tip loaded rotor, now I need to assume or I need to select the total pressure, that is what is expected, or total pressure rise expected at the hub, my total pressure, that is what is expected at the tip, and do not forget we will be doing this total pressure calculation at the outlet as an average total pressure. Okay. So, let us see, say let us assume at hub we are assuming our pressure rise to be 500 Pascal, and at the tip we are considering that to be say 1900 Pascal. It is your choice. Okay. We will see how these numbers they are coming. Say initial calculation with iterations, we have assumed these numbers say 500 Pascal and 1900 Pascal. Okay. So, if I am putting say 1900 Pascal, or say if we are putting at the hub say 500 Pascal, I need to do my calculation at the hub station. Same way for 1900 Pascal also I need to do my calculation at the tip station. Okay. So, let us see what all we are calculating. What we know, my hub, that is what is entry is axial 1. So, I say my alpha 1 at hub it is 0. At hub I can calculate what will be my peripheral speed. Okay. So, this peripheral speed it is coming 19.69 meter per second. We can do our calculation for beta 1 at the hub. So, you can see here this is what is coming say 20.91. So, in line to what all calculation we have done at the mid station, this calculation need to be done at both hub as well as tip. Okay. I can say you do this calculation, but you know it is better to explain, so that will build the confidence in you how exactly this calculation need to be done. Okay, and after building this confidence, you can go further, and that's the reason why we are doing all our calculation at the hub as well as at the tip. So what it says, at the hub we are expecting our pressure rise to be 500 Pascal. So that's what will be giving me my pressure ratio at the hub to be 1.005. Okay, be careful, my pressure ratio at all station, that's what is different. Okay, we have done earlier calculation, that's what is at mid station. Here in this case, I can do my calculation for say temperature rise at the hub. So I will be putting P01 at the hub and delta P0, and this temperature, that's what is, we can say it is 299 K. Okay, and that's what is giving me my delta T0 as 0.49. Okay. Now once we have calculated that part, we can do our calculation based on say our comparison, say aerodynamic work and thermodynamic work, that's what we are comparing here. And based on this comparison, we can do our calculation for say outlet blade angle, okay, or my air angle, that's what is, or relative flow angle beta 2 we are calculating. Now once this is what is known to us, we can calculate what will be my delta beta. Just look at my delta beta is coming 37.18 degree. Same way we can do our calculation, as I told, we need to do calculation for the power requirement at that station also. So this is what is the calculation for the specific energy. Now we can do our calculation for beta 2, that's what is my outlet angle. We can do our calculation for the whirl component, that's what is coming 29.93 meter per second. And my alpha at the hub, that's what is coming, or alpha 2 at the hub, it is coming 33.93. We can do our calculation for relative velocities and relative velocity ratios. So when we are taking these relative velocity ratios at the hub, it is coming 0.97. Just look at. Okay. I am sure you are able to do this calculation. So I am going little fast in sense of showing the calculation. These slides will be with you. Maybe you can verify, you can check also. Here in this case, we can do our calculation for the pitch. Be careful, this is what is for the representation purpose only. You can understand at the hub my radius will be smaller, and that's the reason my pitch will be coming to be smaller. At the tip, my radius is higher, for same number of blades, my pitch will be coming to be on the higher side. So if we are putting here, it says my pitch is coming 0.022 meter. Okay. Now based on this, we can do our calculation for the solidity at the hub, it is coming 2.016. Okay. We can also calculate what will be my diffusion factor. So the diffusion factor based on beta 1 and beta 2, it is coming 0.18. Okay. So my power requirement at the hub station, as we have discussed, that's what is a function of delta T0 at particular station. And if we are taking mechanical efficiency 75% and say my compressor efficiency 85%, it says this is what is coming 4.68 kilowatt. Okay. We can do our calculation for say M factor. Since here, be careful, we are talking about beta 2 at the hub, and that M factor is coming 0.44. We can do our calculation for say camber angle at the hub. We can do our calculation for say deviation angle at the hub, and we can do our calculation for the say stagger angle at the hub. It says this is camber angle is coming 51.12 degree. My deviation angle, it is coming 15.93, and my stagger angle, that's what is coming minus 6.65. Okay. Now in line to that, as we have discussed, we can do our calculation at the tip station also. Okay. So this is what we will be discussing in next lecture. So for today, if you realize what we have done our calculation at the mid station for router 1, and based on that calculation we have calculated all parameters which are required for understanding of design, and we have started calculating other parameters at the hub station. So in next session we will be discussing about the calculation at the tip station. Then we will see how we will be setting with these numbers and why do we need to set these numbers. Then after we will be starting with the design of say rotor 2. So be with me. Thank you very much for your kind attention.